Hello everyone. So I will start my session. My name is Hyuntae Kim. So I am from University of Oxford, and my work is co-worked with Diamond Light Source in the UK and sponsored by the UKRI Engineering and Physical Sciences Research Council. Today I want to talk about system decoupling and control for high-dimensional, high-throughput orbit feedback system. So this is the Diamond 1 plant and goal. So we have a very big storage ring, and we want to monitor this system with beam position monitors with 168 outputs, and we control this system with corrector magnets with 168 inputs. And then we try to design the MIMO controller in 10 kilohertz for this system. We usually describe this system as YS equal to RGS US plus DS. So S is kind of Laplace variables, and for sinusoidal analysis, you can easily set the S equal to J omega. And then each term means that R is the orbit response matrix, ORM, and then GS is a scalar actuator dynamics of the system, and DS is the external disturbance acting on the orbit. So why we need feedback is very simple, that for each storage ring, they have each beamline at the end. So end stations require stable photon beam at source points, and stability translates to data quality and uptime. And then there are many disturbances that ground vibrations or power supply, ripple or RF cooling included lines, and slow thermal drips or the insertion device motion. So there are so many disturbances. So we want to designing a kind of simple controller for this kind of system to mitigate the disturbance. And we try to decouple this R by a single vector decomposition, and we try to use very simple method to each one seesaw loop per mode. And then we choose simple internal model controller as IMC, targets per mode for robust disturbance rejection. I think it's not okay. Yes, okay. So first, I will explain the very simple singular vector decomposition of matrix R, that we have original coordinates planned as YS equal to RGS US plus DS. And then we have a singular vector decomposition of this matrix ORM R, that R is equal to U sigma V transpose. And this U sigma V has very special property that U transpose U is equal to identity, and V transpose V is also equal to identity, and then sigma is diagonalized of the vector sigma 1 to sigma R, so they are diagonalized matrix of sigma, and then sigma 1 to sigma R is kind of, you can line up the value. And then we do the model transform as Y tilde is equal to U transpose Y, and then U tilde as V transpose U, and D tilde as U transpose D. Then we apply this model transform to this plant, then we can get that U transpose Y equal to U transpose R GS US plus U transpose D. And then as using this transform, that tilde Y is equal to sigma GS U tilde S plus D tilde S. So if you think about this dynamics in each line, then this is per mode I is just very simple seesaw system, that YI tilde is equal to sigma IG UI tilde plus DI tilde. So they have each seesaw system, so we can easily design kind of easy controller for this system. But one thing you need to think about is that sigma I has very different value for each mode. So if we just think about very simple step response of the dynamics, then mode 1 and mode 20 has very different value for the sigma I, so they have very different value for this kind of thing. But I don't want to go deep in this robot thing, so I will just skip the detail of the thing. And then by getting that per mode plant, then we do the internal model controller on S3D modes. So we have this YI tilde equal to sigma IGS UI tilde plus DI tilde. And then we design this very simple internal model controller. So sigma IG is kind of plant for this system. And then we think about very ideal mode I models, just same as sigma IG. And then what we need is design this Q filter for this IMC, that QI. So each QI is very simple to design as just signal IG inverse and TS. And TS is a low pass filter chosen for bandwidth and robustness of the system. And then if we just design choosing the low pass filter of TS, then we can get closed loop as very simply that with the nominal copy of sigma IG in the IMC path that like this, then the disturbance to output shape per mode is set mainly by just 1 minus TS. So if you change the bandwidth of the T, then it automatically can deal with disturbance by 1 minus TS transfer function. And then by using this UI tilde, just stack it, and then just using the back map to real actuator, then as the U equal to VU tilde, as the right singular vector basis by the singular vector decomposition, then you get the real controller in real coordinates. So that's the very simple idea of the IMC. So after this IMC method, we upgrade the diamond system to diamond 2. So the diamond 1 has 168 actuator in the system, but we have now 396 actuator as the 252 slow actuator and 144 fast actuator. And then we also increased the BPM as 168 to 252. And then sampling rate is also now 100 kilohertz, and the closed loop bandwidth is have both bandwidth as slow plus fast mode will be handled to 1 kilohertz, and then slow only modes deal with just to 100 hertz. And then time delay is also decreased to 100 microsecond. And then the dynamics of the system also changed, like G is the diamond 1 actuator, and then this green line and blue line is the G as the slow actuator of the diamond 2 and the fast actuator of the diamond 2 system. And then same as the diamond 1, we can write this system as very simply YS equal to RS, GS, US, and then RF, GF, U, and then UF and plus D. So this RS and GS is correspond to slow actuator as the 252 inputs, and then fast will be RF and GF with 144 inputs, and then output will be 252 output of the system. So also in this system, we want to design goal is kind of split control efforts to slow array for the 0 to 100 hertz, and then fast array for the 100 hertz to 1 kilohertz, and avoid the deadband that want to using both fast and slow corrector of the system. And then what we'll do is just expanding our previous idea of diamond 1 of the SVD to the GSVD is the generalized singular vector decomposition of the RS and RF. So we do the generalized singular vector decomposition to RS and RF, then we can get these matrices X and US, or X and UF and sigma S and sigma F. That RS can be written as X sigma S R identity and US transpose, and RF is X sigma F0 and UF transpose. And just same as the single vector decomposition, that US transpose US is equal to identity, and UF transpose UF is also equal to identity, and X is invertible, and sigma and sigma F is also diagonalized, kind of diagonalized matrix with this sigma S1 to sigma S and F, and then sigma S F1 to sigma F and F. So this is you can kind of expanding the result of the single vector decomposition to two matrices, then you can get the GSVD. So one good property of this GSVD is that just same as the single vector decomposition, the sigma S square plus sigma F square is equal to identity, which means that this sigma S parts can distribute their effort automatically in the sense of mathematics. So you can get that by this system that the remaining ny minus nf output directions correspond to the law block. They appear through the identity block in RS, which means in here that these parts only can be dealt with this RS, which means the slow actuator, and then this sigma S and sigma F is correspond to this fast and slow actuator. Both can be dealt with that part. So X inverse is a common off basis that simultaneously diagonalized to two arrays, and fast and F directions and slow fast modes the other ny minus nf directions are slow-only modes. And then for each slow-fast mode I, the pair behaves as a normalized mixing rate between slow and fast actuations. And then we just same as the previous single vector decomposition method, we can get the model coordinates and model planes that we have planned as this. Then we do the GSVD for this system, and then we define the model transform as y tilde as x inverse y, and d tilde as x inverse d, and us tilde and uf tilde as the SVD. And then we just multiply x inverse to the both term, then we can get the tilde y is equal to sigma si gs us tilde and sigma f0 gf uf tilde plus d tilde, which means that if you see this system as per row, then you can get kind of yi tilde for the 1 to nf mode has the both slow and fast actuator appears, but this which means this is a 2-input single output or TISO system. And then for the remaining nf plus 1 to ny will be the gs us j tilde plus dj tilde, which means the just CISO system of the CISO part of the system. And by using this structure, we can design the IMC very simply for this system, that we just set our goal as the TISO modes and CISO modes, that the target TF and TS as bandwidth within 1 kilohertz or 100 hertz. Then we can design the TISO or CISO controller with the idea samely as QSJ and then QSI and QFI is sigma SIG inverse TSS. And then you just minus to the TF minus TS to the fast one, then which reject each one from here, then only TF will remain at the fast actuator row. And then for the CISO system, slow only, so there is only GS inverse TS because there is only identity at the model decomposition. So by this simple IMC structure, we can get slow path tracks TS for the to 100 hertz, and then TF minus TS will be deal with 100 hertz to the 1 kilohertz. And then no deadband because they deal with both bandwidths. So each mode meets its fast target with a clean slow fast split. And then just same as the single vector decomposition, you just stack the system and you just go back to real coordinates, then US and UF will be the real controller for your system. So, and after that, we again upgrade our system to multiple arrays, that if there is 3 slow arrays and fast actuators, like RSI, GSI can be like 3 slow actuators and 1 fast actuator for the system. Then we just using the balancing input filters like US tilde I equal to GSI G S bar USI. Then we can write this system as easily RS GS bar US bar and RF GF UF plus D, which is just same as the 2 slow array system. So and then we can design the same idea at the GSVD, then we can get the controller for the system. So if you're interested in this idea, then you can attend our another paper in this conference at the September 25th about the fast orbit filter using the GSVD for system with multiple slow corrector arrays. And then the key takeaways is Diamond 1 used the SVD for the system, and we can easily design the IMC for each mode. And then in Diamond 2, we also use the GSVD for the RS and RF. Then we can design the IMC very easily for the fast plus slow mode and the slow only modes for the system. And then if there is 3 slow arrays or more arrays, then we can use the kind of balancing filter idea to the system. And then we again get the same controller design by Diamond 2 system as a GSVD. So that's all for the topic that my collaborators Idris Kemp and Stephen Duncan and Paul Glutt from the University of Oxford and Lauren Bob and Shuan Banerjee have with us with Diamond Lysos, and William Heath from Bangor University also helping me. So that's all for today's topic. Thank you for listening.